We are going to take a look at how to solve a consumer's utility maximization problem with Sympy in Python. So we will be using the symbolic computer algebra system that is present in Python to solve this problem symbolically. So the problem is as follows. A consumer has the following utility function, which is a standard Cobb-Douglas utility function x1 to the power a and x2 to the power b. And then the budget constraint is m equals to p1 x1 plus p2 x2. And we need to find the following: the marshallian demand, the indirect utility function, the expenditure function, and the hicksian demands. So we start our work by importing all the relevant packages that we need. So for this work, to solve this problem, I'm just going to import the division, the rational division, and all the modules that are present in Sympy. Then once I have imported Sympy, I'm going to define all the symbols that we need to do this exercise. So I have the two goods x1 and x2, their prices p1 and p2, and we know that in economics we only work with the positive quadrant. So so in other words, our choice of goods cannot be negative, and the prices cannot be negative as well. So I'm forcing these symbols to be positive. And then I have the two exponents and the Lagrange multiplier lambda, and I'm telling Sympy that these are real numbers. These symbols represent real numbers. And then we are going to work with some other symbols, which u for the utility function, m for the budget, v for the indirect utility function or the value function, and e for the expenditure function or the minimum expenditure function. So let's start with defining the utility function. So utility is equals to x1 to the power a into x2 to the power b, and we can see it looks like this. Now we define the budget constraint, which is p1 x1 plus p2 x2, and so this is our budget constraint. And then we are going to construct the Lagrangian, which is simple: L equals to utility plus the Lagrange multiplier multiplied by m minus the budget. So in this case, this is what it looks like. And then we just get the first order conditions. So we differentiate with respect to x1, x2, and lambda, and this will give us three first order conditions. And then when we solve these three first order conditions for x1, x2, and lambda, we will get the marshallian demands. So here I'm just giving the name variable name marshallian to the solution of these three system of equations. So now once Python has solved it, it has saved the solution to this variable name marshallian. And so I'm just saying that the demand for x1, so x1's marshallian demand is equals to, I'm just indexing it. So the first one is going to be definitely x1 here. So we can take a look, and yes, this is the marshallian demand of good x1. Similarly, I'm just assigning x2 mar for the marshallian demand of good x2, and we can also see that this is the marshallian demand of good x2 in terms of prices and the budget m. So the first question is answered: what are the marshallian demands? And then the second question is find the indirect utility function. So we are just going to substitute the value of x1 and the value of x2 into the function, into the utility function. So we have already defined the utility function, so we're just going to say value function is equals to utility with the substitutions. In place of x1, we are going to plug in x1 marshallian. In place of x2, we are going to plug in x2 marshallian, and this gives us the value function. So far so good. Now we need the expenditure function. We can get the expenditure function by just plugging in e in place of m here and setting this equals to u and then solving for e. So that is what I'm doing. I'm saying that expenditure is equals to the solution of u minus the value function, where I'm substituting e in the place of m, and I'm solving for e. So this will give me the expenditure function. Now once I've done the solution, I can see that this is how the expenditure function looks like. So Sympy has not taken simplified all the powers, so we can force it to do it. So we are just saying expenditure 0. This the 0 is the index where this value is saved in the variable expenditure, and I'm just saying that POWSIMP. So this is like simplify the powers, and I'm forcing it to do the simplification. And this is how it looks like once we do the simplification. And then to get the hicksian demands, we can use the Shepard's lemma, that's differentiating the expenditure function with respect to the prices. So I'm just calculating hicksian demand for the good one. So H1 is equals to differentiate expenditure with respect to P1, and I'm simplifying it, and this is how it looks like. And also in this case, Sympy has not simplified the powers, so I can just force it by using power sim, and this is how it would look like once it simplifies the powers. So this looks a bit messy, but let's say if the value of the indices are 1, so if A equals to B equals to 1, let's take a look how the hicksian demand would look like. So we can just substitute A and B to be 1 in our function h1 and just give it the name h1 new. And indeed, this is what we would get if we actually did the math by our hands. So the Sympy is a very good tool to solve analytical models. This is a relatively pretty simple model, but it shows us that Sympy is a very strong tool that we can use to solve complex mathematical models and analytical models that we do.